All right, we're at 20 after, so let's get going here. Welcome to the third installment today, and that's going to cover resilient topologies with event automation. We've got okay, and with Dale Lane, Chief Architect of Event Automation. So, Dale, I'll get out of your way. Take it away.
Brilliant, thank you. Right, hello everyone. Let me just, brilliant. Yes, as you heard, my name's Dale. I'm the Chief Architect for Event Automation. Thank you so much for taking the time to join me for this session today. I should start by explaining that slightly mouthful of a title. What do I mean by resilient topologies? I'm not going to go into a huge amount of detail. This article that I've got linked to here, if you want to dive deeper into it, that's a really good place to go look. But essentially, in a nutshell, what I'm talking about is how do you achieve the sort of availability goals you have, the correctness goals you have in the face of disruptions and outages? How do you keep your service correct, available, durable in response to hardware crashes and outages and all the other sorts of things that can happen? So that's the resilient part. And by event automation, hopefully you've had a chance to see some of the sessions we've been running this week on event automation, or you've had a chance to actually try it for yourself. But there's so many product names around. Let me give you a quick reminder of what I'm talking about. Event automation is a suite of capabilities to help you with an event-driven architecture. It's made up of three components. Event streams, that's your event backbone for managing and distributing and hosting that pipeline of streaming data, real-time data. Event endpoint management brings that kind of sort of API management discipline to your streams of events, so allows you to manage those streams of events as APIs, to document them, describe them, enable access to them in a governed way. And finally, event processing, allowing you to process those streams of events while they're in flight, in motion, in a stateful way, in a contextual way. And that's based on Apache Flink with a low-code UI on top to make it really easy to use. My goal for this session is to sort of touch on all three of these and look at the kinds of considerations for how you can use these three capabilities in a resilient way. I'm not going to make you an expert. We don't have a huge amount of time, but what I want to do is to try to introduce you to the kinds of things you should be thinking about in each of these three technology areas. So introduce you to the kinds of considerations and the sorts of questions you should be thinking about. And if you want to dive deeper into any of these sorts of aspects, please do sort of reach out and we'd love to sort of discuss it in more detail. So this is kind of the big picture we're going to be looking at. And like I say, I'm going to be drilling down into each of the three capabilities and talking about what resiliency means for them in turn. I'll start at the bottom layer, at that sort of foundational layer, which is event streams. Like I say, Apache Kafka, giving you that backbone for your real-time data, your streaming data. So what we're talking about here is how can you make the Kafka service resilient? You've got applications that want to produce, they want to emit real-time streaming data, and you've got applications that want to consume and respond to real-time streaming data. How can you do that in a way that's resilient to disruptions and outages? I'm going to start right at the basics. I'm sure some of you know this stuff already, but it's good to make sure we all have the same sort of common understanding. So Kafka is a distributed service. A Kafka cluster is made up of multiple brokers. And that's kind of the first aspect of where resiliency comes from. What it means is we can tolerate losing individual brokers because they're all peers. And, you know, although there is one controller in the cluster, if the controller goes down, one of the other brokers can take over that role of controller and the cluster remains. So intrinsically, Kafka is a highly available technology, and that resiliency of the service as a whole comes from that distributed nature made up of multiple brokers. That means the service can be resilient, but what about the data that your applications are producing? What I'm showing here is I've got one application producing to a Kafka topic partition, another application consuming those events from the topic. So what does it mean for this to be resilient? Well, the key thing we have is what we call replicas. While this application is producing events to the topic, in the background, we can maintain replicas. We can maintain backup copies, live real-time copies of the events. completely transparent to that application. That application is only needing to talk to the leader, but in the background, these copies are being maintained. And like I said, we call these copies replicas. It's worth keeping in mind because it will help make some of the stuff I say in a moment clearer. When I say replicas, all three of these we describe as replicas. Even the leader is a replica. So yeah, these in terms of terminology, what you're seeing here is three replicas of the streams of events. So what does this mean for resiliency? Well, the reason we do this is so that if anything happens to that replica that the applications are using, that leader replica, if something happens to cause a problem with that, like a hardware outage or a disk failure, that sort of thing, then the applications can just switch over to start using one of the other replicas and seamlessly continue from where they left off. And that's, that gives us a high degree of resiliency because we can switch to our backup copy at any time. And what will happen is that replica that we've switched to becomes the new leader. And the follower that was replicating the old leader starts replicating this instead. And if we're able to restore the system that was hosting the old leader, then that replica becomes a follower. And when it starts back up, it will contact the new leader and catch up on everything that it missed while it was down. So all of this kind of automatically happens and it's baked into the protocol. So applications seamlessly know what to do when this kind of switchover is happening. So that gives us some resiliency. Key thing to recognize, bringing it back to what I was saying about brokers, is it's really important that we put these replicas on separate brokers, because if they were to live on the same broker, then that wouldn't exactly increase our resiliency. So by spreading these replicas out across brokers, that gives us resiliency against a software crash. If anything happens to cause a broker to crash, the other replicas, our backup copies of our data, is available on one of the other broker processes. But more than just resiliency against software crashes, we want to be resilient against hardware failures. So we want to make sure that these brokers are hosted on separate worker nodes. So in the event that something takes out a worker node, so I should sort of back up and say I'm talking in sort of Kubernetes terms here. So you've got your broker pod running on a physical worker node. If anything happens to that worker node, as long as your other brokers are on other worker nodes, your data is still available, you're still resilient. Now, doing all of that is very, very simple. All of it is largely automatic. The only thing you need to do is when you create your topic, you specify how many replicas you want, and all the job of making sure that those replicas are created, that a leader is picked, that the replicas are distributed across the brokers, that those brokers are located on separate worker nodes, all of that is done for you automatically. So it's quite easy to get this sort of first level of resiliency. But I say first level because it's not a binary thing. Resiliency is a spectrum, it's a scale. So let's dig a little deeper into, whether or not this really makes us resilient. So going back to our application that's producing events to our leader, I'm showing underneath here the events on the topic as these lettered blocks, A, B, C, D, E. So what you're seeing here is that two of my replicas are what we call in sync. They've got all of those events, A, B, C, D, E. But one of my replicas has fallen behind. It's got A, B, and C, but it hasn't yet fetched D and E yet. So it's fallen behind. And we would describe this as not in sync. And that's okay, because in the event that we lose the leader, I said before that the applications will seamlessly switch over to a replica. Well, they will switch over to a replica that is in sync. In this case, they'll switch over there. So when the new leader is being picked, what we call electing the new leader, it will be one of the ones that is in sync. But what happens if all of the follower replicas are not in sync? Then we have a problem. Our application is not able to continue. We are no longer resilient. We are stuck. Now, I should sort of say, technically, you can configure an application so that you switch to a not in sync replica. It's not the default behavior, and you probably don't want to do it because it will result in data loss. But if availability is your primary concern, maybe you'd want to do that. But let's assume you don't. Let's assume you don't want to get into this situation in the first place. So how do you do this? It needs more than just creating replicas. You need to configure your applications to use these replicas in a way that will avoid you getting into this position in the first place. two key configs to be aware of here. There's a couple of others, but these are the really important ones. I'll start with this bottom one here, min in sync replicas. What this is saying is this is where you're specifying how many of your replicas should be in sync at a minimum. So what I'm saying here is that I want at least 2 out of my 3 replicas to always be up to date, always be in sync. And this top config, this is a config option for the application, for the producer. And by saying AXOR, what I'm saying is I want to respect the min in sync. And when I'm producing events, I will wait until all of the in sync replicas have got a copy of my event before I think that I've finished what I'm doing, before I continue. So there's a couple of different behaviors that this triggers in the producer application. Firstly, when it's going to produce a new event, it will not. So if you've got this sort of situation where there's only one in sync replica, so the leader has got A, B, C, D, and my 2 followers have only got A and B. They haven't yet replicated C and D. So when the application goes to produce, it will stop. It will throw an error. It will say, I can't produce this topic because it doesn't meet the min in sync. This is intentional. What this is saying is I care so much about the data that I'm going to produce that I don't want to risk putting it on a topic where the replicas aren't keeping up, because I know that means I might lose that event. So this kind of blocking it means that you're not going to make the situation any worse. You're not going to add more events onto the leader if your replication has a problem. So that's one key behavior. And the other characteristic is while it is producing, so say in this situation, the producer produces event E onto the leader replica, it won't carry on until it's aware that all of the in-sync replicas have got a copy of that event E, both of those followers either side. Worth just being totally clear, AX equals all means all of the in-sync replicas, not all of the replicas. So in this situation where you've got 2 in-sync replicas, the leader here and this follower over here on the right, you've got 1 replica that's fallen behind. It's not quite keeping up, but that's okay because the minimum is 2. So you have got that 2. So if this producer was to produce a new event now, event E, it would be waiting for 2 replicas, this one and this one, to get safely write that one to disk before it continued. So by making sure you configure the topic with min in sync and that you configure your applications to respect that, you can avoid getting into that problem where you don't have a viable replica to switch to in the event of a failure. So now, are we resilient? Well, like I say, it's not a binary thing, because what happens if you suffer 2 outages at the same time? 2 disks go down, 2 worker nodes lose their power, 2 network links to worker nodes go down. It's hopefully unlikely, but it's possible. And in the event that you had 2 in-sync replicas, and if you got unlucky and both of those were lost, you would be stuck. So how do you remain resilient in the face of multiple simultaneous hardware failures? The answer is more replicas, more backup copies. So what you're seeing here is a topic that has 5 replicas being maintained. The reason you might do this is because you want to be resilient against losing 2 copies. And with 5 replicas, you can lose any 2 and still be okay. So digging into that a tiny bit deeper, say that if you have your 5 replicas and you configure it to say that the minimum you want to remain in sync at any time is at least 3, you can have a situation like this. And in this sort of situation, it doesn't matter which 2 you lose, you'll always have a viable new leader to switch to. So if I lost those 2, I've got a choice. I can switch to either of the remaining leaders. If I lost those 2, well, there's only 1 remaining replica that's in sync, but I only need 1 to switch to, so I'd still be okay. So it's a spectrum. The more you increase the number of replicas, the more resilient you are, the more you can tolerate more hardware failures, more outages. But obviously that comes at a cost. You're increasing the disk space needed for this topic partition because you're now maintaining 5 copies of all that data. You've increased the network traffic in your cluster because each of these replicas to keep up to date is having to fetch all of those events. So there's a trade-off. The more you increase the resource cost of maintaining a replica, the more resilient you are. So you've got to work out where you're going to make that balance. 3 is a really common compromise. 3 means you can tolerate a hardware outage of a single broker of a single worker node, But if you need that additional level of resiliency, maybe you would look at 5. In theory, you could go even more than 5, but that would be that's very, very cautious. You know, you have to be assuming you're going to be suffering multiple hardware outages at the same time. So now, as long as you set enough replicas, now are we resilient? Well, there's still slightly more to it than that, because I mentioned that we will automatically distribute your replicas so that they are on separate brokers, and we'll distribute your brokers so they're on separate worker nodes. But if all of those worker nodes are hosted in the same cloud availability zone, then if anything happens to impact that availability zone, you will lose all of your brokers, which means you are no longer resilient. So the next step up is to make sure you distribute your worker nodes into separate availability zones, which can be done with Kubernetes. You can make sure that you host your worker nodes, you distribute them across availability zones. And what this means is if you lose a whole AZ, you can still have your remaining replicas, your applications can switch over to them seamlessly, your service is resilient again. It's pretty easy to configure this too. You basically have to tell us what label your worker nodes have to identify what zone they're in. You can see on my slide here, there's a couple of prereqs. The nodes need to be labeled in the first place, but if you're doing Kubernetes across multiple availability zones, you've probably already done that. The only other thing we need is some elevated permissions, because by default, we can't see stuff at the worker node level, so we wouldn't be able to see those labels, so you need to grant some additional roles and role bindings. But once you've done that, it is as simple as telling us what label to look at, and then we'll make sure we distribute stuff across the zones appropriately. So now, does that make us resilient? Now that we've spread ourselves across availability zones? Well, all of those availability zones are going to be in the same region. So anything that, any outage that impacts an entire region will still mean you lose your topics, you lose your service. So how do you remain resilient in the face of the failure of an entire region? The way we do this is what we call mirroring. Mirroring is where we maintain a copy of the topic in a different Kafka cluster, a remote Kafka cluster running in a separate region. The tool we use to do that is something called Mirror Maker. And what that will do is, so as you're seeing here, as before, I've got an application producing events to a topic partition to the leader, and then another application consuming those events. But in the background, asynchronously, without disturbing what those applications are doing, without disturbing the normal replication within the cluster, I've also got Mirror Maker that's consuming all of those events. And as they arrive, it's writing them to a separate Kafka cluster. And we do this kind of mirroring so that in the event that we lose an entire region, we have a mirror, a copy, a remote copy on a separate Kafka cluster running in a separate region, totally isolated from that primary region. So hopefully isolated from whatever caused that major disaster. And our applications can then switch over to using the topics on that backup Kafka cluster. Configuring Mirror Maker is a topic all by itself, and not one that I'm going to have time to get through today. It is very, very configurable. You can choose which topics you want to mirror. Typically, you only do your really critical ones. You can choose what kind of metadata you want to mirror across. Like whether the config for the topics. Things like the offset, which is the bookmarks, the application store of how far they're up to, lots of things like that. If you'd like to know more, I have got a blog post where I go through all of this in detail, and I've actually got a demo that you can sort of deploy for yourself and actually try it out and see for yourself what it feels like to use. But as I said at the start, if you want to dive into any of this in more detail, please do reach out and talk to us, because we'd love to talk about this sort of things. But resiliency for event streams, what does it mean? Firstly, it's worth recognizing Kafka is intrinsically highly available. That distributed architecture of multiple brokers means that you are out of the box before you do anything quite resilient. As long as you create your topics with multiple replicas, that gives you a level of resiliency for your data as well. And as long as you configure your applications to respect that by using things like ACKs and setting your min in sync appropriately, you can make sure that you'll be resilient to hardware failures that affect individual brokers and still be able to carry on what you're doing. And if your data is so critical and your service is so critical that you need to not only withstand individual disk failures or individual power loss, but you need to be resilient even to the extent of losing a whole cloud region, then mirroring is your way of maintaining that copy in a remote isolated region. So that covers event streams. Next, I'll move on to event endpoint management. Pardon me. As I said, this is kind of the API management idea of treating your Kafka topics as if they're an API and managing them in that way, documenting them, describing them, providing self-serve access to them through the gateway. And that kind of brings us to what we want to think about when it comes to resiliency, because I've been talking about how amazingly resilient Kafka is. But if applications are accessing Kafka through a gateway, then it's really important that gateway is resilient to make sure that those applications are always able to access the Kafka topics. So drilling down, what we're talking about here is applications accessing Kafka, and that could be event streams, but equally it could be open source Apache Kafka, it could be Kafka from another vendor, it doesn't matter, we're just talking about any Kafka here. What we're talking about is how do we make sure that if something happens to impact where the gateway is running, that we remain resilient, that applications can keep going. So there's a few options here. Firstly, similar to what I was saying with topics, replicas are a help. You can run multiple instances of the gateway. So what this will mean is when your application first connects, actually, I'm assuming OpenShift here, so I'm saying roots, but equally well, this could be running in a different sort of Kubernetes environment. So that could be like an ingress or something like that. So, but the main point is you've got one connection address in front of all of your gateways. So when a client application connects, it's round robin to one of the gateway replicas, and then that connection gets routed through to that backend Kafka. And remember, like I said, that Kafka could be event streams or a vendor, any other vendor distribution of Kafka. But if something happens to cause that gateway to go down, which could be a crash, it could be the worker nodes it's running on has died, or it could just be something like scheduled maintenance that you need to restart it. Whatever causes that gateway to go away, the application can seamlessly switch over to the other replica and still be routed through. And because that idea of seamlessly switching to a replica is baked into the Kafka protocol, like I was just talking about with event streams, it means applications are just going to do it automatically. You know, it's not something you would need to worry about. It's just part of the Kafka protocol. So how do you do this? From the application side, you just need to configure the client application with that front address that's fronting all of the replicas. So if it's OpenShift, it would be the address of the root. And for when you're deploying your gateways, if you're using our Kubernetes operator to deploy your gateways, it's as simple as just specifying how many replicas you want, and then everything else is handled for you. So that's the first step of how do you have a resilient gateway service, just run multiple replicas. But as I was saying with event streams, what happens if you lose the environment where they're all running? How do you remain resilient even in response to that? Well, you can run gateways in multiple environments. So by multiple environments, this could be Kubernetes clusters running in separate regions, you know, separate Kubernetes clusters in separate regions. So this means you are completely resilient against even the loss of a total region. So the way this would work is the application would first connect to the first environment and be routed through the gateway with all the stuff the gateway can do, like redaction and schema enforcement and all the sort of amazing things the gateway can do to sort of harden your backend Kafka service, and it gets routed through to Kafka. But if anything happens to that gateway, the application will switch to the next environment in its list and then still be routed through to that same Kafka cluster. So how do you do this? From the client application level, you need to give it a comma separated list of the addresses of where the gateways live. The way the Kafka protocol works is it will connect to the first one on the list. If it has any problems talking to the first one on the list, it switches to the second one. And if you've got a third environment, you can have a third comma separated item in the list. It will switch and it will just go through them in sequence. I should sort of say quickly, what this means is you will always use the first one in the list, and then your second environment becomes your backup and your failover environment, only activated in the event of a problem. Now, that's good if you want an active-passive sort of behavior. If you would rather an active-active model where you're using both environments at the same time and then switch them to only use the remaining one in the event of a failure, the way you would do that is just randomize the order of the list, that comma separate list. If you give some of your applications 2, 1 and some of your applications 1, 2, then you'll achieve that idea of using a mixture of the environments all the time. And how do you configure it from the gateway side? Really pretty easy. You give each environment, the deployment in each environment, a unique ID. So you can see here I'm calling the blue environment 1 gateway env1, and I call my green right-hand side environment 2 gateway env2. But I've given both of them the same group name, and that's how you tell event endpoint management that they are all part of the same logical group, so that when you publish something, it will go to all of the things in that group. So it's really simple to achieve this too. So by running gateways in separate environments, it increases the resiliency, so you can handle the loss of even to the extent of an entire region. And the last thing to say on this is you can do both. So you can get the best of both worlds by running gateways in multiple regions, but also running multiple replicas of the gateways in both regions. And it's just a combination of what I said before. So the way you would configure the client application is that comma separated list of the routes fronting each of the gateway deployments. And then it's a combination of the config I've already showed you. So you would identify each environment uniquely with the gateway ID, gateway env1, and you would specify how many replicas you want, replicas 2. And then in the other environment, gateway env2 to identify this environment, and replicas 2. And you might have a different number of replicas in each environment in each region if you wanted. So those are kind of options. It's a lot simpler than what I was going through for event streams. But it's very, very easy to just, by thinking a little bit carefully about where you deploy your gateways, you can make sure that that gateway service is resilient and highly available. So that brings me to the last component, event processing, the ability to use Apache Flink to do real-time stateful processing of events while they're as streaming data while they're in flight. So going back to my overall diagram, what we're talking about here is this Flink service. I'll show you a screenshot of the UI in a moment, but you'll have your low-code UI. You're dragging and dropping nodes on the canvas to describe the kind of processing you want to do. And then when you're happy with it, you're going to deploy that. And then that's going to run your stream processing. And you want to make sure that if anything happens, again, if you lose a worker node, you lose a pod, you have a whatever kind of hardware failure or even restarts or anything like that, you want to make sure that your processing keeps going, that your processing can remain resilient. So for the purposes of this explanation, I've made a slightly contrived flow here. I'll quickly talk through what I've got here. I'm reading from 2 Kafka topics. So the first one, where's my mouse? There's my mouse pointer. So the first one, I'm reading from this topic, and then I'm doing a transformation on all the events I get from that topic. On this second topic, I'm reading from a second Kafka topic, and then I'm filtering out. I'm checking them against some criteria and only keeping the ones that match some filter criteria. I'm then taking these 2 separate streams and I'm correlating them. I'm looking for something that they've got in common and matching them against each other. For all those matches, all those correlations, I'm then aggregating them, grouping them in like an hourly bucket or a daily bucket, some time-based window. And so, you know, think of it as like a running total. I'm counting how many things I see in an hour, or I'm summing all the values I've seen in an hour, or I'm looking at the average or the min or the max, something like that. And then the results are going to a new Kafka topic. Don't worry too much about the details, but just to sort of recap, what I'm saying is I've got one stream of events, 3, 4, 5, 6, 7. I've got blue events that are going through a transform. So I get 3 prime, 4 prime, 5 prime, and so on. I've got this red stream of events, JK, L, M, N, and I'm filtering them. So maybe I keep JK, M, and N, but I filtered out L. I'm then doing correlation. I'm matching. So maybe 3 prime matches against J, 5 prime matches against K and M, 6 prime matches against N. So I'm correlating, I'm matching the 2 streams of events, and then grouping them into, let's say, daily buckets. So I've got my A1, everything that happened the first day, A2, everything that happened the next day, and those are the results going for the sync topic. So when you create a flow like this, what actually happens when you run it? Well, Flink is a distributed system. It's able to scale to very high degrees, and one of the ways it can do that is it distributes. It knows how to break up your job into individual tasks that can be distributed and run in separate places. So at an extreme level, and for a job this simple, it probably wouldn't be split up this much. You know, this job is quite simple. This is unnecessary. But for the sake of argument, imagine that I have one task manager that all it's doing is reading from a Kafka topic and doing those stateless transforms, and then they output the transformed version of the events. I've got task manager one. All it's doing is reading from a topic and then filtering out the ones that don't match the criteria. I've got task manager 2. All that's doing is joining. It's reading from one topic and looking for things from the other topic, from the other task manager that match, and it's correlating those two streams. And then lastly, task manager 3 might be doing that job of aggregating, grouping things into daily buckets so that it's got that running total, that running average, whatever the aggregate you're looking for is. So this ability to distribute the work so you describe the end-to-end processing you want to do, and Flink under the covers distributes that so it can run it at scale, at very, very high scale. The job of splitting it up is the job of the job manager. The job manager takes the description of your event processing and dishes it out. It breaks it down, it decomposes it, and then it distributes it to the task managers. And what we're talking about is in this kind of highly distributed environment, reading from a highly available set of Kafka topics, how do you make sure that if anything happens, say to one of your task managers, that you carry on processing in a way that isn't going to lose data or duplicate data or misprocess data or fail to process data? You want to get the exactly correct results, even in the event of disruption, even in the event of outage. That's kind of what we mean by resiliency in this context. So how do we do that? It's worth pointing out, I'm going to go through the flow again because I showed you with all of the events at once before. And obviously this isn't a batch processing thing. This is stream processing. We're processing stuff while they're in flight. So let me do it slightly more realistically as an event processing flow. So maybe I get the first sort of events. I get event 3 on one topic. I get event J on my other topic. And if you can see the tiny writing, that's sort of like the timestamps that they've arrived. If I move on in time a bit, those events have moved on to the next bit of processing. So 3 is being transformed into 3'. J has been checked against the filter. But while it's doing that, a new event has arrived on one of the source topics. We've now got event 4 coming in. Move a step forward in time again. Maybe that 3' has been correlating. It's been matched against that J. While that's happening, new events are coming in, event 5 on one topic, event K on the other topic. While that's happening, we've just transformed that event 4 into 4'. Move on in time again. That joined where we matched up 3' against J. That's now gone into a bucket ready to be aggregated. It's starting a new set of totals to see if it can be added to anything else. New events are coming in. We're waiting to see if anything matches against 4. Joins don't always match. You know, maybe nothing is going to match against 4, but we're waiting to see what other red events come in to see if we can match it to something. Moving on, we didn't match anything against 4', but we have matched something against 5'. It matches against K, and new events are coming in. L got filtered out. We've lost that. We're now looking at M. That's coming in. That also matches against 5'. So the join is now starting to build up that collection of things that have matched against 5', and new events are coming in. You get the idea. Remember, this is a distributed work. Each of these operators is doing work by itself. It's taking its input, it's doing the stuff that it's been told to do by the job manager, and it's passing on its output. And this allows you to do very high scale, really complex event processing. But it brings us that resiliency challenge of how do you handle that sort of distributed workload in a resilient way? The way we do this is with a technique called checkpoints. So I'm going to go through the flow one last time, and this time I'll show you what we do, what Flink is going to do to make sure that that processing is truly robust and resilient. So this is my flow, and my first couple of events comes in. I've got a blue 3 coming in on one topic and a red J coming in on another topic. The job manager will decide when it's time to take a checkpoint. So maybe it's decided now's a good time. So it's going to inject what we call a checkpoint barrier that I've shown as this blue line into the flow. And this is going to go through the flow. And every time a checkpoint barrier reaches one of the operators, it's an instruction for it to save whatever it's currently doing to some state. And I'm showing the state up top as these kind of gray boxes. So basically it's, what am I currently doing? I'm going to save it up there. So for something like the source topic, it's like, how far have I got through in the topic? We move on to the transform operator. So, we've stepped forward in time, and that checkpoint barrier has flowed through and has now reached the transform operator and the filter operator. So again, they're going to record their state. What are they currently up to? What have they, for something stateless like a transform or filter, there's not a lot of state to record, but it will take its, it will record its state all the same. The thing I want to highlight here is checkpoints don't stop the processing. New events are still coming in. So you can see event 4 has arrived on the source topic. The checkpoint barrier is a moving thing. It doesn't tell the operators to stop what they're doing. It's just saying, while it's processing the events, it should take that point in time snapshot of its current state and record it as it carries on doing its work. So if I step forward in time, you can see now that I've reached the join operator is going to record its current thing. So currently it's matched 3' and J, and it's waiting to see if anything else is going to match. Transform is carrying on processing the stuff it's just got. New events are coming in. Step forward in time again. The checkpoint barrier has now reached the aggregate, which is going to maintain like that daily total of everything that it's seen. It records its state up the top. And lastly, the checkpoint barrier has reached the end of the flow. It's reached the sync topic. What this now means is the job manager has a complete set of state for the entire end-to-end flow. And remember, each of these operators might be running in separate physical machines. So it has done the job of collecting this together across all the different places where this distributed processing is running. And that combined set of state is a checkpoint, and it's going to save that somewhere. And I'll talk in a minute about where does it save it. But for now, just it's enough to sort of think of this is going to be put somewhere safe. But at all of this time, processing has not stopped. Processing is continued. And at some point, the job manager is going to take a new checkpoint. So while processing is continued, a new checkpoint barrier gets injected into the start of the flow, and that will work its way through. And every time it reaches an operator, that operator will record what it's currently doing, its current state. And as it goes through, each operator records its current state until it reaches the end, at which point we can take a checkpoint, that combination of all of that state. So, and a new checkpoint gets started. So why do we do this? What's the benefit of having checkpoints? Well, we do this so that if anything happens, like we need to restart, we've crashed, we need to resume, we're able to restore the state of our processing from the last known good checkpoint. It means that, say, if this was our last good checkpoint, we can load we can tell the source operator, this is where you're up to in the topic. This is where you should pick up from. We can tell this source operator, this is where you were up to on your topic. Oops. We can tell the join operator, this is what you'd currently matched, and you were waiting to see if there was anything else that matched 3'. You can tell the aggregate, you were currently at this state, you were collecting things together into daily buckets, that sort of thing. And actually, that's really crucial because imagine like your aggregate was calculating your daily sales totals. And imagine there was a crash at 10 p.m. You don't want to have to go back and reprocess from midnight till 10 p.m., 22 hours worth of orders to get back to where you were. The benefit of having the checkpoint that will record its state at the point where the last time it had a good state, it can resume from where it left off with all those current running totals, whatever the value of the state was. So if the last known checkpoint was at 9:50 and you're restarting at 10 p.m, it only is going to reprocess those last 10 minutes worth of orders, whatever the source topic state was up to at the point the checkpoint barrier flowed through there. The idea of the checkpoint reflecting a really organized, coordinated snapshot, by doing it for flowing the barrier through all of the operators in turn, it means you get a consistent representation of what the flow was doing at a given point in time. And it means that you can resume from that in the event of any kind of outage or restart or crash or anything like that, and pick up where you left off. So I talked about we're going to store some state and we're going to store checkpoints. So actually, let's get back to that and talk about, well, where do we store it? What does that mean? Firstly, let's talk about state. So just to recap, state is that while the barrier is flowing through, each of the operators is asked to record its current state. It's what I'm representing as those grey boxes at the top. So where do we put that? Well, you've got a couple of choices. You can either store that in memory, what we call hash map. Under the covers, Flink is a Java thing, so it is a Java hash map that's being used. Or you can store it in RocksDB. Why would you pick? Well, HashMap is really, really fast. So if performance is your primary concern, you'll probably pick HashMap. But because that lives in memory, that gives you like a fixed upper limit of how much state you can store. And if you've got a really, really complex operator that is, asking that task to do like maybe you're doing some really complex windowing where you're keeping track of lots of different things that are in flight and you need to store a huge amount of state, that's when you might pick RocksDB, because RocksDB can spill over onto disk. It gives you much, much more space. As long as you've got the disk space available, you can store as much space as you need. You don't have, it's okay to use HashMap for the state, because remember, in the event that something dies, say if you die at this point while the checkpoint barrier was halfway along, this is only a partial checkpoint. You are not going to be restoring from there. You're going to restore from the last complete checkpoint. So it's okay if you lose those bits of state that were in flight. You only need to hold on to them long enough till the end of till the checkpoint barrier reaches the end, at which point it is safely stored into a checkpoint. So it's okay for state to be in memory. And like I say, you do get a performance bump from it. So unless you think your state is going to be too big to fit, you probably want to pick HashMap. But when the checkpoint barrier reaches the end and you're going to save that complete checkpoint, you need that to go somewhere safe. So your choices, again, you can store it in memory on the job manager, or you can store it to disk, safely on disk to some distributed file system. Here, you almost certainly want to write it to disk, unless it's a dev test kind of scenario where you don't really care about the data. If you store it in memory in the job manager, then when the job manager restarts, you've lost your checkpoints. So that's obviously not giving you a lot of resiliency. So you can choose between in memory on the job manager or on disk, but you probably want disk. The other consideration is how frequently do you want to take those checkpoints? So I showed you very frequently, as once the checkpoint barrier reached the end, the job manager injected a new barrier at the start again. I did say that checkpoints don't stop processing, but they're not free. There is a performance cost. There is a cost to that capturing the state, the additional traffic of copying it across. So there is a trade-off between the more frequently you checkpoint, it means that in the event of a restart, you've got a very recent checkpoint available to go back to. So going back to my example of if you're processing orders, if you checkpoint every 5 minutes, then the most you're going to have to reprocess is 5 minutes worth of orders at the absolute worst, because you'll know you'll have a good checkpoint at least 5 minutes ago. If you checkpoint more frequently, say if you checkpoint every minute, then you'll only have to process at most 1 minute's worth of orders, but you've got that additional performance here of doing that sweep across that coordinated snapshot every minute. So there's a balance, and and it's the kind of thing you will want to do some performance testing to sort of see where the trade-off for you is. The configuration for doing this, I'm sort of showing you the two extremes here. So at the top, I'm storing the state in memory by saying state backend is a hash map. I'm storing the checkpoints in memory on the job manager by saying storage is job manager, and I'm doing that. Is that every minute? I can't part. It's in milliseconds, so whatever that many milliseconds works out to. And there's a couple of different, I haven't sort of touched on this, but you can specify the level of orchestration, the usage of transactions, whether or not you want at least once, which means after a restart, you might get some things processed again, or if you really, really need it to be rigorously exactly once, you can specify that, but obviously there's additional overhead in terms of the performance impact. And that's what I'm showing down below. Storing the state in RocksDB so you can tolerate much, much bigger states. Storing those checkpoints safely on a distributed file system so that they're resilient across restarts, and taking checkpoints every 5 seconds. So there are other options. I said at the start, I'm not going to have time to make you an expert in all of these techniques, but what I want to hopefully do is to give you a feel for the kind of thing that's possible and the work that's involved in enabling this. So with event processing, the key approach to resiliency here is checkpoints. Checkpoints give you that automated way of periodically taking a snapshot of that distributed processing. Even though the processing is happening on separate physical machines, it's a way of coordinating, taking that coordinated snapshot so that you have a consistent set of state to restore from in the event of an outage. So that was a lot to go through in a short amount of time. So to recap, event streams, building on Kafka's intrinsic, highly available nature, as long as you are careful with your application design to use replicas sensibly, and as long as you specify how many replicas you want and how many you want to maintain in sync at all times, that gives you a good baseline for resiliency. On top of that, you can distribute your brokers into multiple AZs. And if you really need more resiliency than that, then you can maintain a remote mirror using Mirror Maker. With event endpoint management, the gateways that your applications connect through, you can run multiple replicas and you can distribute them in multiple availability zones and regions to give you a really high degree of resiliency. And lastly, event processing, that Apache Flink, that distributed processing, by using checkpoints and by configuring checkpoints appropriately, you can make sure that that distributed processing remains resilient. So even in the event that you lose individual task managers, your processing can still continue. And with that, I will stop and see if there are any questions. I see there's one question asking for the URL of that blog post I shared. That is a good point. I will dig that out and put it in the chat. And while I do that, hopefully, if anyone else thinks of other questions they've got, please do ask. It is with the blog. There's the one. Oops. See my desktop there, right, and I will add that as a reply in the chat. Please do give it a try. What you'll find there is, as well as blog posts with diagrams explaining the ideas of Mirror Maker in a bit more detail than I've gone through today, you'll also find an Ansible playbook that will automate deploying an active and a passive and a bunch of applications, so you can actually try it out and see what happens when you're maintaining a mirror. And then there's an Ansible playbook for taking out your active region and then doing that failover and switching all your apps to that, so you can actually sort of see exactly how it works for real. It takes a bit of time to set up, but it is worth that kind of hands-on experience. Is really good for having a feel for what mirroring means for real. And as I said at the start, if you want to talk about any of that in more detail, please do reach out for us. It's the kind of thing we love to help people get started with.
Very cool. Anybody have any other questions? We're running a little ahead, but that's okay. Instead of having 5 minutes to jump, we'll have a few more. So be sure to answer the poll, the exit poll for this session. Dale, that was awesome. I was amazed at how well I could hang with you there. It's like, oh yeah, availability zones. That's cool. So very good, very easy to get your hands around. So our next session is going to start at 25 minutes after the hour, and it's going to be our final installment on monitoring of event automation. So join us at 25 after the hour, and we will get into monitoring event automation. Dale, great job. Thank you very much.